Okay, I'd like to welcome everyone to SIS 3021, Lecture 11. So our topic today is minimum cost flows. We'd like to provide an introduction to this topic by looking at a definition for minimum cost flow models in the context of a particular example, and then sort of a formal setting for what constitutes min-cost flow models in terms of our language of network optimization, and then talk about how we could interpret min-cost flows as a particular example of an optimization problem. So we'll be following material. If you're interested in reading in the recommended text, you could look at chapters 9 or sections 9.1 and 9.2 of Ahuja, Magnanti, and Orland. But the lecture today will be self-contained as always. So a couple of announcements before we sort of get into the meat of the material. So assignment 4 and assignment 5 are both due on the 11th of October. That's this coming Thursday. I think I'm going to have a little extra office hours tomorrow morning, Wednesday morning. That'll be announced by email. So I'll be around at 9:30 tomorrow morning if anyone has some questions. That I think those extra hours might help a little bit in giving people some extra opportunity for contact before those two assignments are done. And let's see, on assignment number 5, I wanted to mention that as of this past Sunday, that assignment was revised to remove the last problem, which had to do with our topic today of min-cost flow. But we didn't want to have that on assignment number 5. That'll come later, assignment number 6. So if you've already worked on it, just save it. All right, so let's turn now to min-cost flow and speak a little bit about a particular example known as the Distribution Unlimited Company example. So this is our going to provide our motivation for min-cost flow. And the idea is that we have a company that has two factories, F1 and F2, producing 50 and 40 units respectively. Let's say per week, because the production is on a time basis. And those products are shipped to two warehouses, W1 and W2. W1 requires 30 units per week, and W2 requires 60 units per week. And there's something called a distribution center, which we'll call DC, which can act as a transshipment node for the flow of products from factories to warehouses. So we're going to look at a picture of what this really looks like here. So we've got our two factories, F1 and F2, and you can see the amounts that they're producing, the two warehouses in terms of their requirements for receiving goods, and then the distribution center, which has the opportunity to receive material from both Factory 1 and Factory 2, and then it can ship it out. And as it turns out, the distribution center can only ship to W2. It just doesn't have any kind of transportation link to reach W1. All right. So, oh yes, one other thing to point out is that we have the opportunity, if we'd like, to ship products from Factory 1 to Factory 2, but not the other way around. There's no corresponding arrow in the opposite direction. For the warehouses, we have the opportunity to ship items back and forth between the warehouses, which could be a useful thing. So there is, however, a per unit cost for shipping items along an arc. So the cost is $200 per unit to ship from F1 to F2, $900 a unit to ship from F1 to W1, and so on, as shown here. Okay. And then one more thing is that there's an upper bound on the maximum number of units that can be shipped from one place to another for a couple of the transportation links. So F1 to F2 is limited to 10 units maximum, and the distribution center to warehouse 2 is limited to 80 units maximum. And all the other links, we can assume, have no finite upper bound. So you can send as much as we like along any of the other links. Okay. So if we wanted, we could represent the problem this way, which is sort of a little bit more compact way of representing all the data that we just saw on the previous slide. So C is obviously standing for cost, and U is standing for the upper bound or capacity associated with the link, and we're using these heavy arrows into the node F1 and nodes F1 and F2 to represent the amount of goods that those two factories can produce, and the heavy arrows out of the warehouses to denote the amount of goods that those warehouses must receive. And so then the notion we can think of perhaps some sort of liquid, flowing at the rate of 50 gallons per minute or per week, let's say, into F1, and it has to be distributed through the network and eventually come out of the other end of the network on the pipes that lead out of W1 or W2. That's a nice way to think about it in terms of a physical analogy. Though of course we don't really have that kind of physical structure for the decision problem at hand. Okay, so here's a potential solution to this problem. So ready, here comes. I'm gonna set the amount of flow that's happening on each one of the arcs. So on the arc from F1 to W1, I'd like to send 30 units of flow. On the arc from F1 to DC, I'd like to send 20, and also the arc from F2 to DC, I'd like to send 40. And then you notice that we have 20 going into DC and 40 going into DC. It's probably not a surprise that I'd like to send 60 out of DC to W2. So I want to claim that this is a solution. So I actually don't have to check anything. Oh, by the way, that the assumption is that the amount that we're sending from F1 to F2 is 0, and from W1 to W2 and vice versa is also 0. So I want to claim that this is a solution. And actually, I don't have to do anything fancy to convince myself it's a solution, because anytime I specify values for the arcs in a network, for a flow problem, I've specified a solution to the problem, because the problem is to find the flow values for arcs that have a certain property. And so just writing down any numbers for flow values on the arcs constitutes a solution. In this case, however, what we have is a feasible solution. So what is feasible? Well, if we think about things in physical terms, in terms of the products that are actually being made, that if F1 is producing 50 units at its factory, what we need to see is 50 units coming out of that factory. Otherwise, what's going to happen? Well, if less than 50 units are coming out of the factory is eventually going to just fill up with stuff and blow up. And if if more than 50 units are coming out of F1, then what's going to happen is, eventually it's going to empty any spare inventory that might be in the factory, and I guess it'll kind of implode and wink out of existence and tear a hole in the space-time continuum, something like that. So something horrible. So we have intuitively the notion that from a physical perspective, whatever is produced at factory 1 has to leave, exactly that amount has to leave the factory. And in terms of this network flow model, that means that whatever goes into a node like F1 has to come out of a node, has to come out of that node, the same amount. So that's true for F1 for sure. If we look at F2, there's 40 going in on this dark arrow here, and then 40 going out. So that's good. If we looked at the distribution center, there's 60 going in and 60 coming out. If we look at W1, there's 30 going in and 30 going out. If we look at W2, there's 60 going in and 60 going out. Okay, so this is a feasible solution. If you wanted to know, is it the best feasible solution, then we're talking about how much the solution actually costs. And so because in a problem like this, what we're out to do is to minimize the total shipping cost. And so we could calculate the cost of this solution simply by taking the flow on every arc and multiplying it by the per unit flow cost on the arc. So for example, from F1 to W1, there's a per unit flow cost of 900, and we're sending 30 units along there. So that contribution to the cost is 30 times 900. And we do that for every single arc. And we'll end up with, if you do the arithmetic, you're going to end up with a total cost of 53,000. And you could say, okay, well, what do you think of that? And maybe there's a better solution. So I could try and do something like send more flow along the top arc. That might not be a great idea, but we'll see. And end up shipping some of that extra 5.5 that I sent along the top arc down to W2 instead of sending along this route. So if I do that, I've defined a new solution. It's also feasible because it has the property that what goes into a node equals what goes out, and there's one more property that we need to have that I didn't talk about for the last solution in terms of feasibility, but it's really important, is to make sure that on no arc do we exceed the upper bounds. Well, that really only matters on the arc from F1 to F2 and on the arc from DC to W2, because everywhere else the upper bounds are infinite. But on these two arcs, clearly we have an amount of flow that's less than what we could handle. So in F1 to F2 we have a 0 flow in our current solution. We could handle 10. And from DC to W2 we have a flow of 54.5, and we can handle 80. So this solution is feasible, and its cost is 56,850. So it's actually, I think, more expensive than the first one we had. Here's another solution, and this one you might like because it's not sending very much along that very expensive top arc. So in terms of cost, this might be better. It's feasible. You can verify it in much the same way as we did before. And then if you do the arithmetic, you'll find its cost is 49,000. That might actually be the cheapest flow. More on that in a little bit when we look at some solutions to optimization problems that would give us the solution to this min-cost flow model. Okay, so we'll come back to solving these kinds of problems, but let's just characterize what the problems really are about. So the nature of a problem like this is the routing of stuff from one place, supply locations, to another set of places, demand locations. Given that the stuff that we're routing is going to incur a cost per unit along each of the links that we use. In the Distribution Unlimited company, I say it was $900 per unit sending stuff along the top arc. So we're going to have costs like that. And then, of course, we're going to have capacity constraints on the flows along each of the arcs. Sometimes those will be really large numbers, effectively infinite, and sometimes there'll be small numbers that really might end up constraining what we're allowed to do with a given arc. So if we wanted to think about this model in its most general terms, what we're doing is routing stuff from sources of stuff to destinations for stuff with per unit flow costs, capacity constraints, and adding one more feature that we didn't have on the previous slide, but we've already talked about, which is, well, actually we're going to add two more features. One is a notion of conservation of flow. So we're going to ensure that what goes into any node has to equal what goes out. And then we're going to add one additional feature that we haven't yet talked about, which is the notion of a minimum required flow along arcs. So a lower bound constraint. So for every arc then we can specify the minimum amount of flow that we can have on the arc and the maximum amount of flow that we can have on the arc. So that's a very convenient modeling construct, as we'll see. But there's just an awful lot of problems for which we'd like to start off saying, hey, here's a minimum amount of flow that can go on the arcs in addition to the upper bounds. Okay, so in words, what we're going to say is that a minimum cost flow model is something that's defined on a directed graph where every arc ij has a minimum flow requirement Lij that's non-negative, and has an arc capacity Uij that's greater than Lij, so it's also non-negative but might be something positive, and has a per unit flow cost Cij. And then every node can either receive exogenous flow, so it can be a source of flow, or it can ship exogenous flow, so it can be a sink, or it can be neither and act as a transshipment node, like DC did in the Distribution Unlimited Company example. And we're going to denote through the values for parameter BI whether each node I is a source, a sink, or a transshipment node. So sources are going to have a positive B, sinks are going to have a negative B, and transshipment nodes are going to have a B that is exactly equal to 0. Okay, and then so if we take all those things together, then what we can say is that our problem is to satisfy flow requirements with minimum cost, subject to conservation of flow, capacity, and lower bound constraints. See, it just occurred to me that maybe I'm cutting off the bottom of the slides with our current recording window. So let me do that there so you can see that bottom part, at least for the moment. Okay, so and thing is that that's a very general kind of specification for the min-cost flow problem. And it's kind of abstract in its specification, and it's important that you understand that if we were going to actually make this such a problem statement real for Distribution Unlimited Company or for any other kind of example, then Cij, Uij, Lij, and Bi would be known constants. They would be numbers that we would have to be given in order to formulate and solve the problem. And that the only decision variables are the flows on each arc. We don't even have notation for that, but that's our job, is to choose the flow on each arc subject to the constraints that we don't violate the lower bound or upper bound or conservation of flow ideas, and with the objective of minimizing overall cost. Okay, let's see. One thing to note is that when we specify a model like this, we haven't placed any restrictions on the per unit flow costs. So theCij's can be positive, negative, or 0. That's an interesting thing, because in the text there's an assumption that all costs are non-negative, and the reason is that the text makes that assumption is because anytime one has a min-cost flow model with a negative cost, there is a conversion process that one can go through to convert it to a min-cost flow model with a non-negative cost. It's actually kind of interesting that that works for min-cost flow models but doesn't actually work for shortest path models. So we'll have to think about why that is true a little bit later. We will learn that trick, okay, and we will be able to take any model that we formulated with negative cost arcs and turn it into a problem with all non-negative cost arcs. And it's actually a pretty simple thing to do. But for modeling convenience, we'd like to keep around the notion of negativeCij's for a while. We don't want to restrict ourselves to non-negativeCij's, because we're going to have that trick later, right? So while one can say, without loss of generality, I'm always going to deal with positive, with non-negative costs. Sometimes it's nice when you're modeling stuff to have negative costs, and then realize when you want to solve the problem, you can go ahead and convert it to a problem that has only non-negative costs, if you happen to have an algorithm like we will that only works on problems that have non-negative costs. Okay, so bottom line takeaway is we will work with negative numbers for now, and later we'll show how we can get rid of them and have an easier time with the algorithms. Okay, so the formulation as a picture for a min-cost flow model looks something like this, where on every single arc, say the arc from 1 to 4 in this example, we've got the cost of that arc, C14. We've got the upper bound on that arc, U14, and the lower bound, L14. Notice the L14 here. If you can see, the L really looks like a 1. That's just the font that, I guess it's Times New Roman font or something like that, that where the ones and L's, lowercase L's, are pretty much indistinguishable, to my eye anyway. So 3 numbers, okay, a triplet of numbers for every single arc, and a little bit of weirdness when you look at the order in which those numbers are written. So we're always going to write the numbers in a particular order. We're always going to write cost upper bound, lower bound. And why do that? I mean, it seems a little bit odd, like it somehow would be more natural if we were to say cost lower bound, upper bound. But it's convenient to have cost upper bound, lower bound, because what we can do is drop the lower bound a little bit later. So once we'll get to a point when we're ready to do algorithms where we'll show how we can convert any problem that looks like the one that's shown here to a problem that has 0 lower bounds. And then it's kind of nice just to think about, okay, we're just dropping the last number. It's like it wasn't even there. So we'll get to all that. But in the meantime, stick with this cost upper bound, lower bound. The other thing that you should take note of is that every single node has got a heavy arrow drawn into it. This is a little bit different than what we had with the Distribution Unlimited company, where we had the warehouse nodes with heavy arrows coming out of them. If we want to specify min-cost flow models generally, let's adopt the convention that every single node is going to have a heavy arrow going into it, and we'll let the sign of the number that's on that arrow actually indicate whether the corresponding node is a source, a sink, or a transshipment node. So if we have flow into a node, in other words, the node is a source for flow inside the network, then we're going to have a positive value for B. If we have flow going out of the node, so the node is a sink for flow in the network, then B is going to be negative. And if we have a node that's merely a transshipment node with no exogenous or endogenous flow, then its B value will be 0. So if we put Distribution Unlimited company in those terms, this is what it would look like. It has all the characteristics that I just described. It's got, for every arc, a cost, an upper bound, and a lower bound. And you can see for every arc in this problem, the lower bounds are 0. And a lot of the upper bounds are infinite. And we have two arcs, where there's finite upper bound, 1 to 2 and 3 to 5. And then, yes, again, the other thing to note is every single node has got a heavy arrow going into it, and we're letting the coefficient on that arrow, or the value on that arrow, indicate whether the corresponding node is a source, a sink, or a distribution center. So a 0 corresponds to a distribution center. There's neither flow entering nor leaving the system at that point. So that's node 3 with its nice 0 there, and node 1 here has got a heavy arrow with a 50 on it. That means it's a source. Node 5 has a heavy arrow with a minus 60 on it. That means it's a sink. It's going to absorb 60 units of flow and send them outside of the system. So that's our notation. Okay, it's pretty simple once you get the hang of it. All right, so that is min-cost flow modeling. So we've got a nice model of a nice new kind of network problem that we've never seen before. It's quite different than the shortest path model. It involves things that we can think of in fluid terms, flowing through a network. And the interesting thing is that in general, we wouldn't expect the fluid flow in a minimum cost flow problem to define anything like a path. We might have a number of different paths associated with where the flow is actually non-zero. So we'll get that idea as we kind of go along. So then someone could come along and raise the question, hey, this course you're taking is supposed to be deterministic optimization. Actually, we call it deterministic decision models, but if you said optimization, everyone would agree. And you're studying this min-cost flow model. How do we know that min-cost flow is an optimization problem? So I want to make the argument that it actually is, and that we could represent a minimum cost flow model as an optimization problem. So the notion goes like this. Let's define an optimization problem where we have a decision variable, xij, for every single arc ij that's in our min cost flow network problem. So if there exists an arc ij in that network problem, then we're going to have a variable xij in our optimization problem, and we'd like to interpret xij as being the amount of flow sent from node I to node j. So that's going to be our kind of mental, mental association for xij, but the math will speak to itself, and you'll see that xij is going to play that role mathematically, independent of what sentences we might write down or think about. Okay, we're going to constrain the xij's to be non-negative. We're going to say that xij, in fact, maybe do a little bit better than that. We're going to say that xij is less than or equal to uij, where uij is some non-negative number that's specified for every arc, which is the capacity constraint or upper bound. And we're going to say that xij is greater than or equal to lij, where lij is a non-negative number representing the lower bound amount on arc ij. And then, okay, so that's good. That keeps xij from being too big or too small relative to the network problem that we're trying to capture. And then the other thing that we have to make sure of is that the xij's have a special relationship, that they satisfy conservation of flow, so that whatever gets shipped into a node, I guess I better not do that, whatever gets shipped into a node has to come out of that node. So if you look at, say, node I here on the slide, what is going into I? Well, first thing is there's bi, and then there's a bunch of flow potentially on arcs that start somewhere else and go to I. So say that there's a node j that has an arc from j to I, then the flow along that arc is flow that's going into node I. And if I wanted to say, let us represent all the flow that's going into node I, then what we would do is say, okay, well, it's the bi, that I know is going in, plus the flow on every arc ji, such that ji is in the arc set. So we're going to look at all the arcs that start at some node j and go to I, and we'll add up all their flow values, and that's what's meant by this sum right here. Okay. Oops, sorry. Maybe that wasn't highlighting, wasn't a good idea there. Hold on a second. Okay. All right, and then, whoa, sorry, I'm completely out of control. Bear with me. There we go. And then the other thing we need to look at, I guess I'll just maximize it for the moment, is what goes out of node I. And what goes out of node I is everything that flows out on arcs that originate at I and go to some other node j. So it's all arcs that look like ij, where I is the I that we're talking about and j is some other j in the network, and the arc ij exists in our arc set. So we want to sum over each and every arc that emanates from node I and goes somewhere else. And we want these two things to be equal. So we want there to be a left-hand side, which is what goes in, being equal to a right-hand side, which is what goes out. That is a requirement on the xij's. That's what corresponds to the physical notion of conservation of flow. And if we were to rewrite these equations, what we could do is subtract out the right-hand side from both sides, and then subtract out the this term, the first term, the sum over all the xji's from both sides, and then we have the sum over all xij's minus the sum over all xji's being equal to bi. So again, that means this is everything that goes out minus everything that comes in from other nodes in both cases has got to be equal to the exogenous flow, as a way to think about it. It's kind of an elegant way to think about it. Okay, so what we're out to do in terms of an objective function is to minimize Cij times Xij. So that is simply the cost per unit flow on each arc ij times the amount of flow xij on that arc, summed over every single arc in the problem. Okay? So it's kind of a, whoops, sorry about that, I know how loud those beeps are. So it's a very formidable looking optimization problem at first glance until you get the hang of it. But I think you'll be able to soon look at this kind of structure and get the idea how you could write down particular numbers for a particular problem. So for distribution unlimited company, we can do that. We can look and see we can look and see what the numbers would be to make this into an optimization problem. So there's some easy parts to doing that. So 200x12 plus 400x13 plus 900x14, etc. That's simply the cost per unit flow on arc x1 on arc 12 times the amount of flow x12 that we put on that arc, plus the cost per unit flow 400 that's on arc 13 times the amount of flow that we put on arc 13, which is x13, and so on, summed over all the arcs in the network. And that's clearly the objective function. And then if we look at something like, let's take this this constraint here that says x12 plus x13 plus x14 minus 0 is equal to 50, and see if we can figure out where in the world that constraint came from. If we look back at our picture for, oh, I'm so sorry, I beeped again. If we look back at our picture for the distribution unlimited company problem, and we look at node 1, we can say that, sorry, I'm really out of control, the mouse. If we look at node 1, we can see that, hey, what goes out of node 1 is x12 plus x13 plus x14, whatever those flow values happen to be. When someone chooses the x values, that's going to be what's going out of node 1, and what comes into node 1 is 50. So having 50 equal to the sum of the x's over these three arcs seems exactly right. And likewise, we should have 40 plus x12 being equal to x23. Let's go to the optimization model and see if that's true. So what did I say? 40 plus x12 is equal to x23. Yeah, that's what's captured in the second equation. It's rearranged a little bit. It's rearranged to put all the constants on the right-hand side, but which is a convenient form. We do that often. But it's the same thing as saying what goes into node 2 is equal to what goes out of node 2. Okay, so we have one of these conservation of flow constraints for every single node in the problem. And then we have constraints that ensure that the upper and lower bounds for our problem are satisfied. So we constrain the x's to be non-negative because in this problem, what we're interested in is, are solutions that have just a 0 lower bound. So there's no positive lower bound for any of the arcs. And we're always going to assume that flow is non-negative, and sometimes it has to be a little bit more than non-negative and has to respect some positive lower bound, but not in this case. And then on the arcs 1, 2 and the arc 3, 5, there are particular upper bounds that are finite and need to be satisfied, and those are captured by these inequalities here. Okay. All right, good. So let's talk about some properties of min-cost flow models. So down at the bottom, it's a little bit sliced off, but I think you can see it. Maybe I should just do this. We can see a little min-cost flow problem. It's like the tiniest min-cost flow problem in the world. It only has two arcs. It only has two nodes, and it has one arc. And we can see that there's an exogenous flow into node 1 that's equal to 5. And there's an exogenous flow out of node 2 that's equal to 5. And there's a cost per unit flow of 1 on the arc that goes between 1 and 2, an upper bound and a lower bound, upper bound of 1 and a lower bound of 0. So we can see that it's really necessary for the B's for any min-cost flow model to sum up to 0 if we're going to have feasibility. So we can never have a problem where the B's sum up to something other than 0 and have the problem be feasible. But it's quite possible, as this example shows, that we could have a problem where the sum of the B's is equal to 0 and the problem is infeasible, because indeed this problem is infeasible, right? There's no way that you can send 5 units of flow into node 1 and get them across the network to node 2 where they could be drained out of the system, simply because the arc in the middle doesn't have the capacity. It can only take 1 unit of flow. So there's no feasible solution to this min-cost flow model. It's necessary that the B's sum up to 0, but it's not sufficient. Okay? All right. So far we've thought about min-cost flow in terms of the routing of liquid. It's a great analogy, great way to think about it. It's what, liquid is what you think of when someone starts talking about flow. At least that's what I do. So I think that is quite natural. But there are a lot of situations where we'd like to model processes and events and systems and so on that have the characteristic that the stuff that we want to have flowing around the network is not actually infinitely divisible like a liquid, that maybe it has to come in discrete chunks like minivans or widgets or aircraft carriers or something like that, that really can't be divided up infinitely small. Sometimes we can get away with having to worry about something like that because sometimes we can think of time averages of even discrete things like minivans. And so you could say, well, you couldn't, it's kind of weird to think about making 0.37 minivans. One could say, I average 50.37 minivans a week, okay, in terms of my production facility. So that kind of statement makes sense, saying that, well, sometimes it make a little bit more, sometimes it make a little bit less, but on average, it's we produce 50.37, even if we do everything in terms of whole numbers every single week. Okay, so what's the point of all that? Well, there's something very interesting that happens in min-cost flow models with regard to whole numbers. So I want you to look at distribution unlimited company problem, and I want to show you a bunch of different solutions to variations of that problem. So the original problem that I gave had B values that were 50, 40, 0, minus 30, and minus 60, as shown right here. Okay, and the optimal solution to that problem looks like this. Okay, now what I want to do is show you a change in the value of the B's. So I'm going to change the numbers a little bit and change the 40 to a 39, change the negative 29, the negative 30 to a negative 29, and so on. A little bit of change in production and demand amounts. Okay, so the exogenous flows changed a bit. They still sum up to 0 though now. And the question is, what's the optimal solution for that new set of data? And that's shown right here, 0, 41, 9, 39, 80, 0, 20. And then we could do it again, change the numbers, and we get an optimal solution that's shown here. And do it a third time, and change the numbers, and the optimal solution is shown here. And then, there's a question at the bottom of the slide. Do you notice anything weird about that? And what's the story? And the story is that the peculiarity that we're trying to get at here is that every time we choose different values for the B's, we end up getting solutions that have integer values. Okay, so the amounts of flow that we send on every arc are integer valued at optimality. So the very best solution happens to be a solution where this whole issue that I just raised about whether we should be dealing with discretely defined things like integers because we're constructing minivans or aircraft carriers or something like that really doesn't apply, because almost by accident or just somehow all the answers that we've seen so far have turned out to be integer valued, all the optimal solutions. So it turns out that's not actually an accident. It's a very deep property called the integer solutions property. And the integer solutions property says that if we have, for a min-cost flow problem, if we have integer valued exogenous flows So all of our b's are integers. There's no 3.27 kind of number there, or pi, or any kind of number that's not an integer. All integer valued b's, like we had on the previous several examples. And we have integer valued lower bound constraints and integer or infinite upper bound constraints. Then, if the problem has an optimal solution, it has an optimal solution that's integer valued. So that's kind of a lot to say. It's kind of a mouthful to say at first, but we can break it down. So all I'm saying is that for every problem that has an optimal solution, there is an optimal solution that is integer valued. So that doesn't mean that every optimal solution is integer valued, merely that there exists an integer valued optimal solution. There might exist other solutions that are just as optimal, because sometimes optimization problems, as we know, can have multiple optimal solutions. And some of them can be integer valued and some of them could not be. That's a possibility here. Okay, and then the other sort of caveat in the statement is that if the problem has an optimal solution. So it might be that the problem has no optimal solution because it's not feasible, or because it is feasible but it's unbounded. Okay, so why do we care about the integer solutions property? And the answer is because it allows us to get away with an awful lot in terms of min-cost flow formulations. So we can use min-cost flow models to do things like model the capstone assignment problem, which we'll consider in a little bit. And that's a problem in which what we're trying to do is make assignments of people to projects. And in that kind of world, it doesn't really make sense to think about fractional flow values. We have to have an integer valued solution. And it turns out there are rich classes of problems where we need to have an integer valued solution. And what's neat about the integer solutions property, it says, hey, you know what, you're going to get one, and if you have the right starting conditions, and you don't even have to make a constraint to ensure that it's true. You could just treat the problem like you weren't interested in integers at all, and yet at the end, magically, integers will show up all over the place. It's an incredibly important problem that you're going, or property, excuse me, that you're going to have to really get your head around. In fact, it's so important that I would say, somewhat tongue-in-cheek, that if you're ever asked on a 302-1 exam for the answer to just something and you absolutely just can't think of anything else, then say the integer solutions property, since you're likely to be right more often than you are to be wrong. So it's that important, or it's that key and fundamental to a lot of the things that we're doing. Okay, good. So let's see where we are in terms of a roadmap. What we're going to do for the next few lectures is focus on applications of min-cost flow models. So today was just an introduction, and we're going to look at a number of different examples of min-cost flow models and try and work our way up to the point where we can begin to formulate these problems with some confidence. So you're going to be spending a lot of time thinking about just how to take a word problem, do the same sort of thing that we did with shortest path and other problems, which is to convert it into a particular mathematical structure, the particular mathematical structure of a min-cost flow model. And we're going to, in doing that, take the integer solutions property for granted. That is to say, we're going to say that it is true. It's true, and we won't worry about proving it, because as it turns out, we're going to develop a little bit later two different kinds of algorithms for solving min-cost flow models. And those algorithms, just by their very nature, will allow us to prove the integer solutions property. So like when we get done deriving those algorithms, what you'll be able to say is, yes, I understand that the integer solutions property really holds, and I can tell you why it holds in some level of detail. So that's going to be kind of an interesting thing that comes out of our algorithm development. We'll end up proving this big theorem that we've been taking for granted about integer solutions. So we're going to end here, And I want to thank everyone for your patience in listening to this video. Don't know how it turned out. This is my very first YouTube video. I could see myself recording many YouTube videos in the future and maybe building up a whole um, empire of YouTube videos on the basis of Systems 3021. Or maybe not. Maybe I won't get any big time advertising sponsors for this activity. But let's what we'll do later is probably do this one more time and maybe try and raise the production quality a little bit, and then get some feedback on how it would work if we took this kind of format and used it as the basis for the delivery of lecture material and sort of as the basis for talking slides that you could refer to anytime in the future, and then spent more time in class just working out freehand responses to questions or clarifications on this concept or that concept, or review of homework problems, or any of the other things that we could think of doing if we weren't constrained to have the lectures. So that'll be a survey that we do a little bit later, and we'll see how it goes. So again, thank you very much. I look forward to seeing everyone in class on Thursday.